and welcome to Algebra II with Mr. Clausen. Today I'm going to talk about quadratic regressions. And so specifically what I'm going to do in this video is I'm going to go over how to do a quadratic regression, specifically using a TI-84 emulator with a physics example. And then the second skill of this video, I'm going to talk about how to do a quadratic regression using Desmos. So what I would like you to do is that if you are using Desmos as your graphing technology, I want you to skip to skill 2 and walk through that example, take some notes about how to do these regressions, and then with those notes, I want you to follow along with skill 1 to get yourself acclimated with how to use the technology. Now, if you're using a TI-84, I want you to just continue to skill 1. I want you to take notes about how to use the technology to do a quadratic regression as you're watching the video, and then just let the video continue on to skill 2 with the second example, and then just try to solve it and go along accordingly. So with that said, let's get started here. Alright, so if you watched the Desmos example already, awesome. You can pause it here if you want, and then just go and answer the question. Give yourself some practice in looking at this. But if you're using a TI-84, take careful note because I'm going to walk through how to analyze this specific question. So when you're doing a quadratic regression, and we're going to use a TI-84, what you're trying to do is you're trying to take this set of data, you're trying to plug it into a TI-84, and then use that to create a regression that you can then use to find something else. So for this given situation, we have a man that throws a ball off the top of a building. The table shows the height of the ball at different times. Create a model using a quadratic regression and determine the height of the ball after 2.5 seconds using your modeled equation. So we can see that we're looking for a height between these 2 points, but we don't have it. We could try to guess and extrapolate and say, and somewhere in the middle, just pick a number, but we want to be precise, and we can be relatively precise by creating a model. And so if we're looking at a man throwing a ball, let's say he has this ball here, and he's going to go and throw it, and he's on top of a building. All right, so if he's on top of the building, we can see that the height of the ball at the top of the building is 46 feet. Because at 0 seconds, that's where the ball is. Now he throws the ball, it has a parabolic trajectory, and it eventually crashes. So after 1 second, we see that the ball has a height of 63 feet, which is being represented by this maximum height, and this occurs after 1 second. And so what we're going to do is we're going to create a function in standard notation of a quadratic, and then we're going to use that quadratic to answer the question at hand. So with that said, let's go, and I'm going to switch over to a TI-84 emulator, and I'm going to walk through how to create this regression. Alright, so what I'm going to do here is I'm going to use this TI-84 emulator, and this is just a pretty standard calculator used in most Algebra II courses. And so what I'm going to do is I'm going to show you how to do this regression. So much like we've done previously, if you hit the stat button, you can go to these program lists, and we have edit. We're going to need to input this list in terms of time and height into our list. So we're going to need to edit that. And so what I'm going to do is I'm going to use X, or list 1, as my time, my independent variable, and I'm going to say that the height of the ball is dependent on the time that the ball is in flight. All right, and so I'm going to go my 0, 1, 2, 3 for my X values, and then for my Y values, the original height of the ball, the maximum height of the ball, at least that's documented, the descent onward down, and then after 3 seconds, it's only 1 foot from the ground. And now I've inputted this data that we are given in the original problem. So we are well on our way of modeling this quadratic equation. So now that I've inputted this, I'm going to just hit second and quit. And so that edited list is in there. And now that it's in there, we're going to toggle over to calc. So I'm going to hit this arrow and I'm just going to move over. And what I've shown you in the past is that I've asked you to go to linreg to do a linear regression. Well, to do a quadratic regression, you just go down one more and you do a quadreg, all right? And so after seeing this, you're probably seeing cubic and quartic, and you have all these other types of regressions at your disposal. But specifically, I'm just going to do the quadreg. And so with this quadreg, it automatically places the x as list 1, the y as list 2, and we're going to go and we're going to calculate this regression. And so now it goes and it spits out the A term, the B term, and the C term for this regression. You'll notice that the standard function notation is used here, and now we have these values. So we have these three terms that we get from our calculator, and now all we need to do is plug the A and the B and the C into their appropriate places, and we will get a quadratic regression. We will get a model of a quadratic equation. So now that we have this model of this parabola, this quadratic function, we can now use this to find other pieces of information. For example, time is x and height is y. So if I want to find the height of the ball after 2.5 seconds, all we need to do is plug 2.5 in for x and solve as such. So now that we have this, we'll just say that when x is equal to 2.5 seconds, we can now solve for y at that given point. Or maybe we want to say f of 2.5. Just use f of x to describe this. Maybe use the function notation to our benefit here. And in this given circumstance, negative 16 times 2.5 squared plus 33 times 2.5 plus 46. And when you do all the math for this, you will find that this equals 28.5 feet once it's all said and done. So I'll leave you to use your calculator to do the plug-in and chug-in and just to check that answer. But we can use this to go and model equations and then find outputs based on hypothetical circumstances that we don't have a given data point for. So with that said, I'm going to move on to the next example, and if you're using a TI-84 right now, you can actually go along with this other example and give it a try yourself. Alright, so now what I'm going to do is I'm going to do a quadratic regression using Desmos with this communication example. And so if you just got done with the TI-84 example, you can just try to pause the video and try to walk through this and do it on your own, or just have it playing as you're doing it. Either way is fine. Just want you to get some practice. If you're using Desmos, and Desmos is going to be the technique that you're using in class, I want you to watch this. I want you to take very careful notes, and then at the end of the video actually go back to skill 1 and try to do that one on your own. But on the table I have here, what I want to point out is that the table here shows the percent of U.S. houses with cable TV. Now, this is probably truly parabolic because, I mean, who has cable TV nowadays? I mean, everyone's got Netflix and all these other network subscriptions, and, I mean, having cable TV is kind of more of a luxury more than anything. But I digress. So if we want to find a quadratic model to describe the data, we'll have to do a regression. And then with that, we can estimate the percentage of households with cable TV in 1995 using our model. Okay, and so you'll notice that in the 1960s, if we set 1960s as our origin, we'll see that in the 70s it went up and then kind of peaked, and then it's coming back down. And we're going to assume this parabolic behavior. We're going to assume a standard function notation can be used of ax squared plus bx plus c can be used to analyze how this might look. And guesses are that they're assuming that things are peaking around 2000. You know, so if this is the year 2000, maybe we can set that as our 68%. We'll just have to see kind of how this turns out. But the one thing I'm going to tell you to keep in mind before I switch over to Desmos is that we're going to set the year 1960 as x equals 0. All right? And so in this given case, if this is x equals 0, this would be x equals 10, this would be x equals 20, and so on and so forth. Don't put it in as 1960, 1990, and so on and so forth. You are just creating such a hassle for yourself. I've seen so many students do it, and they get these super bizarre functions, and they can really just have simplified their lives if they just did this horizontal shift and they did this. So I'm going to switch over to Desmos and show you how to do this. All right, so I have Desmos up now. I left the data on the bottom so you can clearly see all that as we're going through it. And we're going to treat this much like a linear regression that we did in Unit 3. So we're going to put a table here, and I'm going to put the years in the X column here. And I'm just going to do that thing I suggested earlier, set it up. And one of the really cool things is once you start setting a pattern, it a lot of times predict it for you. That makes putting in your X values really quick and easy. And now I'm just going to start putting in some other data here. And it is this simple as far as putting in your lists in Desmos. So right now we're just plotting that data. And if we go over, we can click the little wrench icon and we can set up our x-axis here. So let's go from -10 to 50. We'll do increment steps of 10, and that'll just set it up so that we can clearly see at 0, 10. And we actually see one of our data points here. And then what I'm going to do also is I'm going to set the y values from, again, let's go -10, and then go up to 100, because 100% would be everything. All right, and we'll do this again in steps of 10. Let's just keep it super simple as far as the values. And one of the things that you're going to notice here is that we have the data for these 5 years in place. All right, and so we have some really easy data to look at visually, and so as we start making our functions, we can kind of get an idea of what that looks like. So to graph this, or to do the regression, remember that we just simply put in the variable that we want to have compared in terms of the y terms, and instead of doing equals, you have to do the tilde, and then we're going to start putting everything in now in terms of function notation. So we'll go ax, and we want to compare to the values in x1, and we're going to square that term just like with function notation. And then we'll go and we'll add, and we'll go bx1, and we'll leave that to the first power, and then we'll add c. And now you can see that we have this general parabolic curve, and you might not be able to tell it's a parabola because we're so zoomed in, but if you zoom out, you can see you have just part of the parabolic curve showing here. Now, obviously it does go back down at some point, but in terms of looking at the short range amount of data, the parabolic curve fits this data really well. It fits it with 95.93% goodness, a fit, so to speak. So the r-squared value is 0.9593, which means that less than 5% of the data points would be considered outliers. So, and that's really good. You want most of your data to fit your trend line really well. And so then you have the A, B, and C parameters here, and you have these very specific values. So now we can go and we can plug these terms in for A, B, and C we can create a modeled quadratic function to represent these data points. So now that we have these parameters, we can now create the modeled equation. So we can say y is equal to 0.02357 x squared plus 0.90714 x minus 2.08571. And we have a modeled equation that will give us an output of percentage of households with cable TV based on the number of years after 1960. All right, so now to answer this question, it's important to keep track of your variables and what they mean. But if we want to know what the data says at 1995 or at that year, we'll just say when x is equal to 35, which based on a horizontal translation is the year 1995, we can then plug 35 into this function and solve for it as such. So let's go y, and actually let's use the f of x notation, and let's say f at 35, and we'll plug 35 into this function. So we'll go 0.02357 times 35 squared plus 0.90714 times 35 minus 2.085, or let's go 6. Let's just round it a little bit just so it all fits there. And if I go and I solve all this out and I get an output, I will find that 58.5% of households have cable TV in 1995 based on my model. All right, and so all this is really giving you an opportunity to do is take some data, perform some inductive reasoning, and see if we can make an educated guess about what the percentage would be. So with that said, I hope that you found this video helpful. If you are using Desmos as your graphing technology, please go back to skill 1 and try to answer that one using Desmos. And if you're just going through the video using a TI-84 and you're practicing on this, that's great. I hope that you found this video helpful and it gave you a better understanding about how to do quadratic regressions using Desmos or the TI-84. And with that said, let's do some math.